In this last lecture, we are going to give a classical description of the spinning photon. Remember that the most general elementary particle in the relativistic case has 10 kinematical variables. But in this case, the velocity is going to be a constant vector, so the only kinematical variables we have are time, the position of a point, and the orientation of a Cartesian moving, rotating frame attached to that point. Now that point is moving at a constant velocity c. So the general form of this free photon Lagrangian is this one. There is no term in the acceleration. And the nether constants of the motion, as before, are these ones, but here what is left is the capital U functions which appear here. And now the spin is only the W part. Now, in this model, because S equals to satisfies the same equation as before. But now the difference is that U is a constant vector and P is another constant vector. So this is very far from being an elementary particle if P and U are not collinear, because this cross product will define a constant vector, and this system will represent an object whose spin is continuously increasing. But if it represents an elementary particle, this spin must be constant, so P and U must be collinear. In that case, the spin is a constant vector. Okay. If we take the time derivative of k, since SU are constant vectors, we get this. Kp, in fact, has along the direction of the velocity of the point, and taking the scalar product of this with U, take this form. Well, this is in fact the energy and linear momentum of a photon related to the velocity of that photon. Now, these two satisfy this invariant equation, and therefore this object is a massless object. It's a massless particle. So the description of an object of this kind represents a massless particle. From L, we see that we have this general form, but because P is this one, and H is this one, and T is minus H, and R is P, we see that the first two terms of the Lagrangian are this. So this vanishes. Okay, if this vanishes, it represents that our free Lagrangian is only reduced to the last term, the term related to the angular velocity. This is important because W is the spin of the system. Well, if the spin is not transversal, as we would see before, we can see here that the formalism forbids the existence of massless point particles without rotation. Because if we have spinless particles moving in a straight line, this will mean that if W is 0, there is no Lagrangian, so there is no mechanical system. To be L different from 0, necessarily the particle has to have spin. So if we consider that the spin is not transversal, so the spin is U over C is a unit vector along the velocity times the modulus of the spin and perhaps a plus or minus sign, according to the spin is pointing forward or backward. Now, from this Lagrangian, the linear momentum is this derivative of the L0 with respect to the velocity. We take this form, and the spin, of course, is the partial derivative of L0 with respect to omega, what we have seen as a definition of the spin. But you see, P is along the velocity, so the omega has to be necessarily along the velocity. And the spin is also along the velocity, so because the Hamiltonian is this, if I take the scalar product of this with U, it's equivalent to take the scalar product of this with omega. So the Hamiltonian can be written in both forms. The particle is a positive energy particle, and P and U have the same direction. S and omega have the same direction, and because omega has the direction of U, because it's proportional to the linear momentum, a spin and angular velocity for the photon has necessarily the same direction, either pointing forward or backward. So the four vectors are collinear and constants of the motion. Now the energy of a free photon is positive, and if we write it in this way, because these two vectors are collinear, this is the scalar product, is the product of their modulus, the modulus S, the modulus of omega, which can be written in those periods, 2 pi, as 2 pi the frequency. Now, if we accept Planck's hypothesis that the energy of a quantum of light is Planck's constant times its frequency, we get that 2 pi s is Planck's constant, so that the spin of this classical model necessarily is Planck's constant divided by 2 pi. The photon is necessarily a boson, and the possible values of this particle is necessarily plus or minus h. What we have here is a photon moving along a straight line with the angular velocity rotating along that direction, pointing forward or backwards. So it is rotating leftward, rightwards, or leftwards. So a beam of monochromatic photons, all with the spins in their same direction, corresponds classically, in the electromagnetic point of view, to a circularly polarized monochromatic wave, right or left according to the spin direction. Well, all this formalism is written in this monograph and also in these lecture notes. Of course, I lecture at the University of Basque Country. You can contact me, and with this we finish this didactic introduction to general formalism for describing classical elementary spinning particles, of which we have analyzed the electron and the photon. Thank you very much for your attention.